The sun is on fire, not metaphorically, not approximately. At its core, temperatures reach 15 million degrees Celsius, a number so extreme that the human brain has no instinct for it, no framework, no reference point built from daily experience. 15 million degrees. The surface of the sun alone, the part we can actually see from 93 million miles away, burns at roughly 5,500 degrees Celsius. Hot enough to vaporize iron. Hot enough to reduce any known solid material on Earth to plasma in fractions of a second. And yet, right now, somewhere between Earth and that nuclear furnace, there is a region of space where the temperature hovers near absolute zero, the coldest state matter can theoretically reach. Minus 270 degrees Celsius, a fraction of a degree above the point where all molecular motion stops entirely. Not cold the way Antarctica is cold. Not cold the way the upper atmosphere is cold. Cold in a way that has no analog in any human environment. A cold so complete and so uniform that it stretches across billions of light years in every direction. The sun is screaming energy into space at a rate of 3.8 times 10 to the 26th watts, 380 septillion watts, every single second. It has been doing this for approximately 4.6 billion years, and the space surrounding it is, for all practical purposes, frozen. How is that possible? That question is not rhetorical. It is one of the most genuinely disorienting facts in all of astrophysics, and the answer dismantles something most people believe they understood since childhood, the idea that heat naturally spreads, that fire warms its surroundings, that proximity to something hot makes you hot. On Earth, those assumptions are correct. In space, they collapse completely. To understand why, it helps to start not with the sun, but with what heat actually is. Heat is motion. That is not a simplification. It is the precise physical definition. The temperature of any substance is a measure of the average kinetic energy of its particles, atoms and molecules in constant chaotic motion, vibrating and colliding and transferring energy to neighboring particles through those collisions. When you touch a hot stove, the rapidly vibrating metal atoms slam into the atoms of your skin, transferring their energy directly. That is conduction. When you sit near a fireplace and feel warmth on your face without touching the flames, the heated air molecules between you and the fire carry energy to your skin through the movement of the air itself. That is convection. Both of those mechanisms, conduction and convection, require matter. They require particles to collide, to transfer kinetic energy, to physically move from one place to another carrying heat with them. Remove the matter, and both processes stop entirely. Space is not empty in the poetic sense. It contains magnetic fields, charged particles streaming outward from stars, faint wisps of hydrogen atoms separated by enormous distances. But for the purposes of heat transfer, it is functionally empty. The vacuum of interplanetary space contains roughly 5 particles per cubic centimeter. Compare that to Earth's atmosphere at sea level, which contains approximately 2.7 times 10 to the 19th molecules per cubic centimeter. The difference is not a matter of degree. It is a difference of 19 orders of magnitude. If the density of Earth's atmosphere were the population of the entire observable universe, the density of interplanetary space would be a single person. With so few particles present, conduction and convection become essentially irrelevant. The sun cannot warm space the way a radiator warms a room because there is almost nothing there to warm. There is a third mechanism of heat transfer, and it is the only one that functions in a vacuum. Radiation. Electromagnetic radiation. Light, infrared, ultraviolet, X-rays. Every object with a temperature above absolute zero emits electromagnetic radiation, and that radiation travels through vacuum at 300,000 kilometers per second, carrying energy outward without needing any medium to move through. The sun radiates energy across the entire electromagnetic spectrum, and that radiation does travel through space efficiently. When it strikes a surface, the skin of an astronaut, the hull of a spacecraft, the regolith of the moon, it is absorbed and converted back into heat. But here's the critical detail. Radiation heats surfaces. It does not heat the vacuum itself. The photons streaming outward from the sun pass through space without interacting with anything, because there is almost nothing to interact with. They do not warm the sparse hydrogen atoms drifting between planets in any meaningful way, because the collisions are so rare as to be negligible on any practical timescale. The vacuum between a radiating object and a receiving surface stays cold, regardless of how powerful the source. This is why a thermos bottle works. The vacuum layer between its inner and outer walls prevents heat transfer, not because vacuum is cold, but because vacuum cannot conduct or convect heat, and minimizes radiative transfer between the two surfaces. Take that principle and scale it to the distances of space, and the paradox resolves itself. The sun's energy is real, immense, and constant. The space around it is cold, not because the sun is weak, but because cold and hot are properties of matter, and space has almost none. The moon is perhaps the most dramatic illustration of this on a human scale. The moon has no atmosphere. Its surface faces the sun directly, and in those sunlit regions, temperatures climb to approximately 127 degrees Celsius, hot enough to boil water. Step around to the side, permanently facing away from the sun, or drop into the shadow of a crater at the lunar poles, and temperatures plunge to minus 173 degrees Celsius. The same world, a few hundred kilometers apart. A temperature difference of 300 degrees, because without an atmosphere to distribute heat through convection, each square meter of lunar surface is either irradiated or completely isolated, nothing in between. Astronauts on the International Space Station face a version of this constantly. The station orbits Earth at roughly 408 kilometers altitude, completing one full orbit every 90 minutes. In sunlight, the exterior hull can reach 121 degrees Celsius. In Earth's shadow, it drops to minus 157 degrees Celsius. The station transitions between those extremes 16 times every 24 hours. The engineering required to manage that thermal cycling, insulating materials, heat pipes, massive radiator panels, represents one of the more underappreciated challenges of human spaceflight. But the story of heat and cold in space does not end with the vacuum of our solar system. The background temperature of the universe itself, the cosmic microwave background radiation, sits at 2.725 degrees Kelvin, or approximately minus 270.4 degrees Celsius. This faint signal is not metaphorical. It is the actual, measurable temperature of the observable universe, the thermal remnant of the Big Bang, cooled over 13.8 billion years of cosmic expansion. Every point in intergalactic space is bathed in this radiation. It represents a hard floor. The coldest the universe will passively allow anything to become without active refrigeration. Even that number tells a story. The universe was not always this cold. In its earliest moments, the first fractions of a second after the Big Bang, temperatures reached values that dwarf the core of the sun by factors that require scientific notation to write. 10 to the 32 degrees Kelvin in the first Planck time. The entire history of the cosmos, from that unimaginable furnace to the near absolute zero background we measure today, is a story of expansion and cooling. The universe itself is an object that has been losing heat for almost 14 billion years. Which raises a question that takes the paradox of the cold space around our sun and scales it to something far larger. If the universe began in a state of near infinite heat, and if heat naturally seeks equilibrium, and if the cosmos has been cooling for billions upon billions of years, why does anything hot still exist at all? Why does the sun still burn? Why do stars form, ignite, and pour energy into a universe that seems determined to cool everything toward absolute zero? The answer involves gravity, nuclear physics, and a process of energy release so violent and so sustained that it has been fueling every star in the observable universe since the first 3 minutes of cosmic history. The question has a history. For most of human civilization, the nature of the sun's heat was not a scientific problem. It was a theological one. The sun was divine, or it was eternal, or it simply was, requiring no further explanation. The Greeks debated whether it was a burning stone or a god riding a chariot. Anaxagoras of Clazomenae, in the 5th century BCE, proposed that the sun was a white-hot mass of metal roughly the size of the Peloponnese, an idea so offensive to religious sensibility that it earned him a charge of impiety and exile from Athens. The notion that the sun was a physical object, subject to physical laws, was not always an obvious or safe conclusion. It took until the 19th century for the question to become genuinely urgent, and the urgency came not from philosophy, but from geology. Charles Lyell's work on stratigraphy in the 1830s established something uncomfortable. Earth's rock layers, sediment deposits, and erosion patterns demanded enormous timescales to explain. The processes observed in the present, rivers carving valleys, sediment compressing into stone, species evolving through natural selection, could not have produced the geological record in thousands or even tens of thousands of years. The evidence pointed toward hundreds of millions of years at minimum. Darwin's theory of evolution, published in 1859, reinforced the same conclusion from a completely different direction. Life's complexity required deep time. That created a direct and devastating problem for physics. If Earth was hundreds of millions of years old, the Sun had to be at least as old. Older, almost certainly, since the Sun predates the formation of the planets. And no known energy source could sustain the Sun's output for that long. The most powerful chemical reaction imaginable, pure combustion, hydrogen burning with oxygen, would exhaust a sun mass of fuel in roughly 10,000 years. The Sun would have burned out before the first complex organisms appeared on Earth. The leading alternative, proposed independently by Hermann von Helmholtz and William Thomson, later Lord Kelvin, was gravitational contraction. As a massive cloud of gas collapses under its own gravity, the infalling material converts gravitational potential energy into heat. The numbers were not unreasonable for their time. A sun slowly shrinking by roughly 40 meters per year would release enough energy to account for the observed solar luminosity. The shrinkage would be imperceptible over human timescales. The total energy available from gravitational contraction for a body the mass of the Sun, however, could sustain the current luminosity for approximately 20 to 40 million years. Kelvin was confident. The Sun was at most a few tens of millions of years old. Geology and biology, he argued, had simply got their timescales wrong. He was one of the most distinguished physicists of the 19th century. He was completely wrong. The resolution came in the 20th century, and it required an entirely new understanding of matter itself. In 1905, Albert Einstein published his special theory of relativity and derived what became the most famous equation in the history of science. Energy equals mass multiplied by the speed of light squared. The speed of light is approximately 300,000 kilometers per second. Square that number and multiply by even a small amount of mass, and the energy released is staggering beyond any chemical or gravitational analogy. 4 years before Einstein's paper in 1901, the French physicist Henri Becquerel had already confirmed that radioactive decay released energy without any corresponding chemical reaction, energy appearing from within matter itself, with no combustion, no oxidation, nothing that classical physics could account for. The atom was not the indivisible fundamental particle it had been assumed to be. It had structure, and that structure contained energy. The synthesis came slowly, through the work of many scientists across the 1910s, 20s, and 30s. Ernest Rutherford's experiments established the nuclear model of the atom in 1911. Francis Aston's mass spectrometer measurements in the early 1920s revealed something extraordinary. The mass of a helium atom is slightly less than the combined mass of 4 individual hydrogen atoms. Not by much. The difference is approximately 0.7%. But Einstein's equation had already established what a tiny difference in mass means in terms of energy. That missing mass, converted to energy at the rate of the speed of light squared, produces an output entirely consistent with the Sun's observed luminosity sustained over billions of years. The Sun is not burning. It is fusing. The distinction is not semantic. Combustion is a chemical process. Electrons rearranging between atoms, releasing energy stored in molecular bonds. Nuclear fusion is a nuclear process, atomic nuclei themselves combining, releasing energy stored in the nuclear binding force. The energies involved are not comparable. A single kilogram of hydrogen undergoing complete nuclear fusion to helium releases approximately 6.3 times 10 to the 14th joules of energy. The same kilogram of hydrogen burning chemically with oxygen releases roughly 1.2 times 10 to the 8th joules. Fusion releases more than 6 million times the energy of combustion per unit mass. Every second, the sun converts approximately 600 million metric tons of hydrogen into helium through nuclear fusion. Of that mass, roughly 4 million metric tons is converted directly into pure energy via Einstein's equation, radiated outward as photons, neutrinos, and heat. 4 million metric tons every second for 4.6 billion years. To make that tangible, the mass of the Great Pyramid of Giza is approximately 6 million metric tons. The sun annihilates the energy equivalent of 2/3 of the Great Pyramid into pure radiation every single second, and it has been doing so continuously since before Earth existed. The sun has lost enough mass through this process over its lifetime to equal roughly 100 times the mass of the Earth itself, and it has barely made a dent in its total fuel supply. It remains approximately 74% hydrogen by mass. The fusion occurs in the sun's core, a region extending from the center to roughly 25% of the sun's total radius, compressed to densities of approximately 150 times that of liquid water and heated to those 15 million degrees discussed earlier. At those temperatures and densities, hydrogen nuclei, single protons, move fast enough and pack close enough together that the electromagnetic repulsion between like-charged particles can occasionally be overcome by the strong nuclear force, allowing two protons to fuse. The primary fusion pathway in the sun is the proton-proton chain, a sequence of reactions that ultimately converts 4 hydrogen nuclei into one helium-4 nucleus, releasing energy at each step. The physics of that barrier, two positively charged protons approaching each other closely enough to fuse despite their mutual electromagnetic repulsion, is itself a story of quantum mechanics. Classically, the protons should never be able to get close enough. Their thermal velocities at 15 million degrees are, by themselves, insufficient to overcome the Coulomb barrier, the electromagnetic repulsion between like charges. The fusion happens anyway, at rates that power the sun, because of quantum tunneling, the quantum mechanical phenomenon by which a particle has a non-zero probability of penetrating a potential energy barrier that classical physics says it cannot cross. Without quantum tunneling, the sun would not burn, stars would not exist, the universe would be dark. This is not a poetic claim. The calculated rate of proton-proton fusion in the sun's core, incorporating quantum tunneling probabilities, matches the observed solar luminosity to high precision. Remove quantum tunneling from the equations, and the fusion rate drops to essentially zero. The warmth on your face on a clear afternoon is the direct macroscopic consequence of a quantum mechanical effect occurring in the cores of subatomic particles 93 million miles away. The energy generated in the sun's core does not escape quickly. A photon produced in a fusion reaction at the solar core begins a journey outward through the radiative zone, the thick shell of dense plasma surrounding the core, that takes an extraordinarily long time. The photon does not travel in a straight line. It is absorbed and re-emitted by charged particles in the plasma almost immediately, at essentially random angles, undergoing a random walk through a medium so dense that its mean free path, the average distance it travels between interactions, is roughly 1 centimeter. 1 centimeter in a region that spans hundreds of thousands of kilometers. The result is that the energy produced in the sun's core takes an estimated 10,000 to 170,000 years to diffuse through the radiative zone to the surface. The exact figure depends on assumptions about opacity and density distributions within the solar interior, and estimates have varied considerably across the literature. Once it reaches the convective zone, the outer 30% of the sun's radius, energy is carried to the surface far more rapidly by convective currents of rising hot plasma and sinking cooler plasma, completing the journey in a matter of weeks. The photons that left the sun's surface this morning, the ones arriving at Earth right now, were generated in nuclear reactions that occurred somewhere between 10,000 and 170,000 years ago. The light you see is ancient. The sun you observe is a delayed image of its own interior, filtered through 100,000 years of diffusion. But here is where the story takes a turn that shook the scientific community to its foundations. If the proton-proton chain is producing energy in the sun's core at the rates implied by the solar luminosity, it should also be producing an enormous number of neutrinos, nearly massless, nearly interaction-free particles that stream outward from the core at nearly the speed of light, passing through the sun's bulk as if it were not there. Unlike photons, Neutrinos do not random walk through the plasma. They escape in approximately 2 seconds. They carry information about the core's activity in real time. In the 1960s, the physicist Raymond Davis Jr. built a detector deep underground in the Homestake gold mine in South Dakota, a tank containing 380,000 liters of dry cleaning fluid designed to capture the rare interaction of a solar neutrino with a chlorine atom. The detector worked. Solar neutrinos were detected, but the number arriving was wrong. Not slightly wrong. The detector was catching only about 1/3 of the neutrinos that solar fusion models predicted should be there. For 3 decades, that discrepancy, the solar neutrino problem, stood as an open wound in astrophysics. Either the models of solar fusion were wrong, or something was happening to the neutrinos on their way to Earth that nobody understood. The answer, when it finally arrived, changed particle physics permanently. Neutrinos are ghosts with mass, not metaphorically. The neutrino passes through matter with a contempt for interaction that has no parallel among the particles physicists routinely study. Every second, approximately 65 billion solar neutrinos pass through every single square centimeter of your body. Through the palm of your hand, through your skull, through the floor beneath your feet, and the rock beneath that, and the entire bulk of the Earth itself. And the overwhelming majority of them interact with nothing. They arrive from the sun. They pass through you. They exit through the soles of your feet heading toward the other side of the planet, and they are gone. You will never feel them. No instrument on Earth can stop them. The best detectors humans have built catch, at most, a handful per day out of the billions streaming through them every second. This near-total invisibility is the direct consequence of the neutrino's fundamental nature. It carries no electric charge, which means it does not interact through electromagnetism, the force responsible for virtually every physical interaction in daily human experience, from friction to chemical bonding to light. It interacts only through gravity and the weak nuclear force. Gravity, at the scale of a single subatomic particle, is negligible to the point of irrelevance. The weak nuclear force has an extraordinarily short range. It operates only at distances smaller than 10 to the minus 18 meters, roughly 1,000th the diameter of a proton. A neutrino must pass almost directly through the nucleus of an atom to interact with it. Given that an atom is mostly empty space, if the nucleus of a hydrogen atom were scaled to the size of a marble, the electron's orbital shell would extend to roughly 2 kilometers away. The probability of any single neutrino hitting any single nucleus while passing through matter is vanishingly small. To make that concrete, a neutrino traveling at nearly the speed of light would need to pass through a wall of lead approximately 1 light-year thick before having a 50% chance of interacting with a single lead atom. 1 light-year of solid lead. The distance from Earth to the nearest star, Proxima Centauri, is approximately 4.2 light-years. A wall of lead stretching most of the way to the nearest star would stop, statistically, about half the neutrinos fired into it. The other half would pass through entirely. This is the particle that Raymond Davis was trying to catch. His detector at Homestake used a specific reaction: a solar neutrino colliding with a chlorine-37 nucleus, converting it into argon-37. Argon-37 is radioactive, with a half-life of approximately 35 days, and Davis's team extracted it from the tank every few weeks through a remarkably delicate chemical process, bubbling helium gas through 380,000 liters of perfluoroethylene to sweep out the few dozen argon atoms produced among the trillion chlorine atoms in the tank. The entire experiment was designed to catch, on average, roughly 1 neutrino interaction every 2 days. Not per second, not per hour, every 2 days. Instead, they caught roughly 1 every 6 days. The deficit was real, reproducible, and stubbornly persistent across decades of operation. Davis ran the experiment from 1967 to 1994, 27 years of continuous data collection, and the result never changed. The sun was producing at most 1/3 of the neutrinos that the standard solar model predicted. Either the model was catastrophically wrong about the sun's core, or something was happening to the neutrinos themselves. The first instinct in the physics community was to doubt the solar model. Perhaps the sun's core was cooler than believed. Perhaps the proton-proton chain was proceeding at a lower rate. This was not an unreasonable position. The interior of the sun was, after all, completely inaccessible to direct observation. The temperature and density profiles used in solar models were inferred from surface observations and theoretical physics, not measured in situ. A small reduction in core temperature, a few percent, would produce a significant reduction in neutrino flux while barely affecting the observable luminosity. But the solar model proved remarkably robust against every attempt to break it. Helioseismology, the study of acoustic oscillations propagating through the sun's interior, analogous to seismic waves moving through Earth, provided a completely independent probe of the solar interior. The sun oscillates in millions of overlapping resonant modes, and the precise frequencies of those oscillations encode detailed information about the density, temperature, and composition of the interior. By the 1980s, helioseismological measurements had confirmed the standard solar model's predictions for the internal structure of the sun to an accuracy of better than 1%. The core temperature of 15 million degrees was not a guess. It was a measurement, made through the analysis of sound waves. The solar model was correct. The neutrinos were wrong. The resolution required a fundamentally new piece of physics, and it came from a concept that had been theoretically proposed but never confirmed: neutrino oscillation. The neutrino does not come in a single variety. There are three distinct types: the electron neutrino, the muon neutrino, and the tau neutrino, each associated with a different charged lepton partner. The sun produces exclusively electron neutrinos through the proton-proton chain. Davis's detector, based on chlorine chemistry, was sensitive only to electron neutrinos. The other two types passed through it without producing any detectable signal. In 1998, the Super Kamiokande detector in Japan, a stainless steel tank containing 50,000 metric tons of ultra-pure water, instrumented with 11,000 photomultiplier tubes, watching for the faint flashes of Cherenkov radiation produced when neutrinos occasionally interact with water molecules, published definitive evidence that muon neutrinos produced by cosmic ray interactions in Earth's atmosphere were changing their identity in transit. Neutrinos were oscillating, spontaneously transforming from one type to another as they traveled through space. Oscillation is only possible if neutrinos have mass. In the standard model of particle physics as originally formulated, neutrinos were massless, and massless particles cannot oscillate between types. The confirmation of oscillation meant the standard model was incomplete. Neutrinos have mass, tiny, almost inconceivably small, but non-zero. The current upper bounds place the mass of the electron neutrino at less than 1.1 electron volts divided by the speed of light squared, compared to the electron, which has a mass of approximately 511,000 electron volts divided by the speed of light squared. The neutrino is at least 500,000 times lighter than the electron, the lightest charged particle known. In 2001, the Sudbury Neutrino Observatory in Ontario, Canada, using 800 metric tons of heavy water, a form of water in which the hydrogen atoms contain an extra neutron, delivered the conclusive answer. Unlike the Homestake detector, SNO was sensitive to all three neutrino flavors through a neutral current reaction that any neutrino type could trigger. The total neutrino flux arriving from the sun, summed across all three types, matched the standard solar model's predictions perfectly. The electron neutrinos Davis had been counting were not disappearing. They were transforming, converting from electron neutrinos into muon and tau neutrinos during the 8-minute journey from the sun's core to Earth, and arriving undetected because every previous detector had been blind to 2/3 of the signal. The solar neutrino problem had not been a problem with the sun. It had been a problem with humanity's understanding of the neutrino itself. Davis received the Nobel Prize in Physics in 2002, shared with Masatoshi Koshiba of Super Kamiokande, for the detection of cosmic neutrinos. Takaki Kajita of Super Kamiokande and Arthur MacDonald of SNO received a separate Nobel Prize in 2015, specifically for the discovery of neutrino oscillations and the confirmation that neutrinos have mass. The solar neutrino problem, which had seemed like an embarrassing gap in solar physics, turned out to be a window into physics beyond the standard model, a discovery about the fundamental nature of matter that reshaped particle physics entirely. The neutrino story does not end there. The Sun produces approximately 3.7 times 10 to the 38th electron neutrinos per second, nearly 400,000 trillion neutrinos every second, streaming outward in all directions at nearly the speed of light. At Earth's distance, the flux is approximately 65 billion per square centimeter per second. Those neutrinos carry energy directly from the Sun's core, escaping in approximately 2 seconds compared to the 100,000-year photon diffusion time. They represent the most direct possible signal from the nuclear engine at the heart of the solar system. Detecting them in sufficient numbers and with sufficient energy resolution now allows physicists to measure in near real time the rates of specific fusion reactions occurring in the Sun's core, distinguishing the proton-proton chain's various branches, measuring the contribution of the carbon-nitrogen-oxygen cycle, which accounts for roughly 1% of the Sun's energy output and becomes the dominant pathway in more massive stars. The Borexino experiment in Italy, running since 2007 beneath the Gran Sasso mountain, has detected neutrinos from specific branches of the proton-proton chain individually, a feat of experimental physics so demanding that the detector required the lowest concentration of radioactive contaminants ever achieved in any large-scale material, reducing the background radiation inside the detector to levels billions of times below that of ordinary rock. The cold of space and the heat of the Sun are linked ultimately not by distance or vacuum physics alone, but by this. The energy that warms Earth arrives as electromagnetic radiation after a 100,000-year journey through the solar interior, but the proof that the engine is running arrives 8 minutes later, invisible as a flood of particles that pass through your body and the entire Earth beneath you without leaving a trace. The Sun's fire is real. Its evidence streams through you right now, and yet none of this explains why the Sun's outer atmosphere, the corona, is hundreds of times hotter than its surface, in flagrant and still only partially resolved violation of every intuition about heat flowing from hot to cold. The corona should not exist, at least not at the temperature it does. The surface of the Sun, the photosphere, the layer that emits the light we see, sits at approximately 5,500 degrees Celsius. Moving outward from the photosphere, the temperature should drop. That is the expectation built into every intuition about heat. The further you move from a source, the cooler it becomes. A few hundred kilometers above the photosphere lies the chromosphere, a thin transitional layer where temperatures rise modestly to around 20,000 degrees. Strange, but not yet alarming. Then, above the chromosphere, the solar atmosphere opens into the corona, and the temperature does not continue rising modestly. It detonates. The corona reaches temperatures between 1 million and 3 million degrees Celsius. In the most energetically active regions, during solar flares and coronal mass ejections, localized temperatures can exceed 10 million degrees. The photosphere is 5,500 degrees. The corona, millions of kilometers further from the core, is 1 million to 3 million degrees. This is not a rounding error. It is not a measurement artifact. It has been confirmed by independent instruments across multiple wavelengths, X-ray observatories, ultraviolet telescopes, radio interferometers, for decades. The corona is genuinely physically orders of magnitude hotter than the surface below it, and for most of the 20th century, no one could adequately explain why. The violation it represents is not subtle. The second law of thermodynamics, one of the most rigorously tested principles in all of physics, states that heat flows spontaneously from regions of higher temperature to regions of lower temperature. A hot object radiates energy to its cooler surroundings. A cooler region cannot spontaneously absorb heat from a hotter region and become even hotter than the source. That is the direction every thermal gradient points, in every system ever measured. The corona reverses it. The surface is hot. The atmosphere above it is hundreds of times hotter. Something must be actively depositing energy into the corona. Energy that does not originate from the photosphere directly, but from some mechanism that bypasses the surface entirely and dumps power into the outer atmosphere. The question of what that mechanism is has occupied solar physicists for more than 80 years, and it remains one of the most actively contested problems in astrophysics. The first person to confront it with data was the Swedish physicist Bengt Edlund, working in 1941. Spectroscopic observations of the solar corona had revealed spectral emission lines, specific wavelengths of light corresponding to the energy transitions of ionized atoms that no one could identify. For decades, astronomers had attributed these mystery lines to a hypothetical element they called coronium, assumed to exist only in the sun's outer atmosphere. Edlan identified the lines as belonging not to any exotic new element, but to highly ionized iron. Iron atoms stripped of 13 or 14 of their 26 electrons. The designation for such iron is Fe 14th, and it can only exist at temperatures above 1 million degrees. The coronium mystery was not the discovery of a new element. It was the discovery that the corona was genuinely millions of degrees hot. The implications landed hard. Here was direct spectroscopic proof that the outer solar atmosphere reached temperatures no known passive process could explain. The corona was not warm. It was a plasma furnace sitting above a surface 600 times cooler. Two broad classes of mechanism have dominated the theoretical debate ever since. The first is wave heating. The sun's surface is violently convective, boiling, churning plasma in constant turbulent motion, with convection cells called granules, each roughly the size of Texas, rising and falling on timescales of minutes. This surface convection drives acoustic and magnetohydrodynamic waves, oscillations that propagate upward along magnetic field lines into the corona. The magnetic field of the sun is not a uniform dipole. It is a tangled, dynamic structure, threaded with flux tubes, coronal loops, active regions, and open field lines stretching into interplanetary space. Waves traveling up these field lines carry energy from the convective zone into the corona. If the waves dissipate their energy at coronal heights, converting wave motion into thermal energy, the corona heats. The specific wave type most favored is the Alfvén wave, a transverse oscillation propagating along magnetic field lines, named after the Swedish physicist Hannes Alfvén, who predicted their existence in 1942 and received the Nobel Prize in Physics in 1970 for that work. Alfvén waves have been directly detected in the solar corona by multiple spacecraft. The Hinode satellite, a joint Japan Aerospace Exploration Agency and NASA mission launched in 2006, returned the first unambiguous direct imaging evidence of Alfvén waves propagating along coronal structures. The waves were real. The question was whether they carried sufficient energy to account for the coronal temperature, and whether the corona's plasma could dissipate that energy efficiently enough. Theoretical models suggest they can contribute significantly, but the precise dissipation mechanisms remain incompletely understood. The second class is magnetic reconnection heating. In regions where solar magnetic field lines of opposite polarity are pushed together by convective motion at the surface, the field lines can snap and reconnect in a new configuration, a process called magnetic reconnection. The topological change releases enormous amounts of stored magnetic energy almost instantaneously, converting it into kinetic energy and heat in the surrounding plasma. Reconnection events on small scales, called nanoflares, a term coined by the physicist Eugene Parker in 1988, may occur continuously across the entire corona in numbers so vast that their collective heating effect is sufficient to maintain coronal temperatures. Parker proposed that the corona is heated not by one large continuous process, but by the superposition of billions of tiny explosive events, each individually undetectable with existing instruments, but collectively dominant. Eugene Parker was not immediately believed. His 1988 paper on nanoflares was initially rejected by the journal that received it. Two peer reviewers rejected the manuscript outright, arguing the physics was wrong. The editor, the astrophysicist S. Chandrasekhar, overruled both reviewers and published the paper on his own authority. Parker's concept now sits at the center of coronal heating research, and a NASA spacecraft bears his name. The Parker Solar Probe, launched in August 2018, is the closest humanity has ever placed an instrument to the sun. Its mission is to fly through the corona itself, not observe it from a safe distance, but physically pass through the outer solar atmosphere, measuring magnetic fields, plasma conditions, and wave activity in situ. To survive proximity to the sun that would vaporize any unshielded material, the probe carries a carbon composite heat shield 11.4 centimeters thick, facing the sun, while the instruments behind it operate at near room temperature. The shield's sun-facing surface reaches approximately 1400 degrees Celsius. The instruments in its shadow remain at roughly 30 degrees. In its early close passes, at distances of approximately 15 million kilometers from the sun's surface, closer than any previous spacecraft, the Parker Solar Probe detected something unexpected even within the theoretical framework that sent it there. It measured sudden, intense reversals in the direction of the magnetic field, brief flips lasting seconds to minutes, associated with dramatic spikes in solar wind velocity. These structures, which the mission team nicknamed switchbacks, were not predicted in the detail observed. Their origin, their relationship to wave heating and reconnection, and their role in accelerating the solar wind remained under active investigation as the probe continued its trajectory inward toward ever closer perihelion passes. The solar wind itself is a consequence of the corona's extreme temperature. A plasma at 1 million degrees has enough thermal energy that some fraction of its particles, predominantly electrons and protons, achieve escape velocity from the sun's gravitational field. They stream outward continuously in all directions, filling the heliosphere, the vast bubble of solar influence extending far beyond the outer planets, with a constant flow of charged particles traveling between 400 and 800 kilometers per second at Earth's distance. The solar wind was predicted theoretically by the physicist Eugene Parker in 1958, the same Parker of nanoflare fame, and confirmed by direct measurement from the Mariner 2 spacecraft in 1962. The connection between the corona's anomalous temperature and the existence of the solar wind is direct and causal. Without the corona being millions of degrees hot, the solar wind either would not exist or would be far weaker. Without the solar wind, Earth's magnetosphere would be a different structure. The aurora would not exist in their present form, and the entire electromagnetic environment of the inner solar system would be fundamentally different. The inexplicable heat of the corona is not an isolated curiosity. It is the engine of the heliosphere. The mechanism that heats the corona also accelerates the solar wind. How the corona transitions from a bound, hot plasma to an outflowing wind, exactly where and how the energy that drives acceleration is deposited, remains one of the Parker Solar Probe's primary scientific objectives. The probe's orbit is designed to bring it progressively closer to the sun through a series of Venus gravity assists, reaching a minimum perihelion distance of approximately 6.2 million kilometers, less than 9 solar radii from the surface, by the end of its primary mission. At that distance, the probe will be physically inside structures that drive the solar wind, measuring conditions no instrument has ever sampled. The sun has been studied continuously since the invention of the telescope. Galileo observed sunspots in 1610. Spectroscopy revealed its chemical composition in the 19th century. Nuclear physics explained its energy source in the 20th. And yet, in the 21st century, the most fundamental question about the outer solar atmosphere, why is the corona so hot, does not have a complete consensus answer. Wave heating, nanoflare reconnection, or some combination of both. The precise budget of coronal energy input is still being measured, still being modeled, still being debated in the refereed literature. That is not a failure of science. It is science working exactly as it should, pressing instruments closer to the source, refining theories against data, maintaining honesty about the boundary between what is known and what remains open. The sun is 93 million miles away and has been burning for 4.6 billion years, and humanity's most advanced spacecraft is flying through its atmosphere right now, measuring the answer. But the corona is only the beginning of the mystery that cold space presents. Because even if the corona's heat is explained in full, a deeper question waits behind it. One about the fate of all that energy, the direction of the universe's thermal arrow, and what the relationship between heat and cold in space ultimately means for everything that exists. On the 18th of August, 2012, a filament of solar plasma roughly 330,000 kilometers long, roughly the distance from Earth to the Moon multiplied by nearly 900, erupted from the sun's surface in a single sustained arc. The Solar Dynamics Observatory, a NASA spacecraft positioned in geosynchronous orbit above Earth, captured the event in high-resolution ultraviolet imagery across multiple wavelengths simultaneously. The filament rose, stretched, and collapsed back onto the solar surface over the course of several hours. It was not classified as a major event. It was not the subject of emergency alerts. It was, by the sun's own standards, routine. That is the scale of the ordinary. The sun's most violent expressions are coronal mass ejections, eruptions in which billions of metric tons of magnetized plasma are expelled from the corona at speeds ranging from approximately 250 kilometers per second for slower events to more than 3,000 kilometers per second for the most extreme. A coronal mass ejection is not simply a burst of light or radiation. It is a physical displacement of matter, a cloud of plasma the size of a small planet, threaded with magnetic field, hurled into interplanetary space. When directed toward Earth, such a cloud arrives at our planet between 1 and 3 days after leaving the sun, depending on its velocity, and its interaction with Earth's magnetosphere produces effects that range from spectacular aurora displays at high latitudes to, in the most powerful events, significant disruption of electrical infrastructure across entire continents. The most powerful geomagnetic storm ever recorded struck Earth in September 1859. It is known as the Carrington event, named after the British amateur astronomer Richard Carrington, who observed the solar flare that preceded it on September 1st of that year. Carrington was sketching sunspots through his telescope when he observed 2 intensely bright patches of white light appear suddenly near a large sunspot group, the first direct human observation of a solar flare. The coronal mass ejection that followed traveled from the sun to Earth in approximately 17.5 hours, an extraordinarily fast transit that reflects the exceptional energy of the event. The resulting geomagnetic storm induced electrical currents in telegraph lines across North America and Europe, strong enough to shock telegraph operators, to set telegraph paper on fire, and to allow telegraph systems to operate without their batteries, powered entirely by the geomagnetically induced currents flowing through the wires. Aurora were reported as far south as Cuba, the Bahamas, and Hawaii. People in the northeastern United States reportedly read newspapers by the light of the aurora alone. In 1859, the global electrical infrastructure consisted of telegraph lines. Today, it includes power grids, satellite networks, GPS systems, pipeline monitoring systems, and the entirety of digital communication. A Carrington-scale event striking Earth today would represent a catastrophe of extraordinary scope. A 2012 study published in the journal Space Weather estimated potential economic losses from such an event in the range of $1 to $2 trillion in the United States alone, with recovery times of 4 to 10 years for the most severely affected regions. The vulnerability stems from the same physics that makes aurora beautiful. When a massive magnetized plasma cloud sweeps past Earth, the rapid changes in the magnetic field induce electrical currents in any long conducting structure. Power lines, pipelines, undersea cables, at scales that transformers and protective equipment are not designed to handle. The sun produced a coronal mass ejection on July 23, 2012, that was later measured by the Stereo A spacecraft to have been broadly comparable in intensity to the Carrington event. It missed Earth. The ejection's trajectory carried it through the region of space that Earth had occupied approximately 9 days earlier. 9 days separated the most technologically advanced civilization in human history from a potential catastrophe on the scale of the 19th century's most violent solar storm. The miss was not a close call in any human intuitive sense. 9 days is not a narrow margin. But in the geometry of interplanetary space, where Earth is a target roughly 12,700 kilometers wide, moving through an orbital path nearly 1 billion kilometers in circumference, the geometry of near misses is humbling. The relationship between the sun's heat and the cold of space crystallizes most dramatically in these events. A coronal mass ejection departs the sun at millions of degrees. The coronal plasma it carries reflects the corona's extreme temperature at the moment of eruption. As it expands outward through interplanetary space, it cools through adiabatic expansion, the same process by which air expanding rapidly from a compressed canister feels cold against your skin. The plasma cools as it expands into the vacuum, distributing its thermal energy across an ever larger volume. By the time it reaches Earth, approximately 150 million kilometers from the sun, the plasma temperature within the cloud has dropped significantly from its coronal values, though it remains far above any temperature encountered in ordinary terrestrial experience. The cold of space does not destroy the ejection. It dilutes it, spreading its energy across a volume that dwarfs any human frame of reference. This thermal evolution, extreme heat at the source, progressive cooling through expansion, delivery of energy to whatever it encounters at vast distances, is the fundamental story of how the sun interacts with space. Not warming the vacuum, but sending discrete parcels of matter and radiation outward into it, where each parcel's heat gradually surrenders to the cold that surrounds it on all sides. The most extreme expression of this dynamic in our solar system occurs at the heliosphere's outer boundary, the heliopause, where the solar wind's outward pressure finally balances the inward pressure of the interstellar medium, the sparse gas and dust filling the space between stars. The heliopause lies at approximately 120 astronomical units from the Sun, 120 times the Earth-Sun distance, roughly 18 billion kilometers. The Voyager 1 spacecraft, launched in September 1977 and traveling at approximately 17 kilometers per second, crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space. At that distance, the solar wind's temperature and density have dropped to the point where the interstellar medium dominates. The sun's thermal influence ends. Interstellar cold begins. The temperature of the interstellar medium varies widely by region, from extremely cold molecular clouds at approximately 10 degrees Kelvin, through warm neutral hydrogen at roughly 8,000 degrees, to the hot ionized gas of supernova remnants and stellar wind bubbles at millions of degrees. The interstellar medium is not uniformly cold. It is a complex, dynamic thermal landscape shaped by the energy inputs of stars, supernovae, and cosmic rays. But in the regions between these energetic structures, in the dense molecular clouds where new stars are slowly assembling from gravitational collapse, the temperatures approach the cosmic floor, 10 degrees above absolute zero, where molecular hydrogen barely moves, where the chemistry of star formation operates on timescales of millions of years, where the silence between stellar events stretches across distances that light requires tens of thousands of years to cross. It is from exactly these frigid, nearly static environments that stars are born. A molecular cloud dense enough and cold enough will begin to collapse under its own gravity when its thermal pressure, the outward force of the gas's own warmth, can no longer resist the inward pull. The threshold for this collapse is described by the Jeans criterion, derived by the British physicist James Jeans in 1902. A cloud will collapse when its mass exceeds a critical value determined by its temperature and density. Cold clouds collapse more readily than warm ones because cold gas exerts less thermal pressure. The molecular cloud's extreme cold, its proximity to absolute zero, is not an obstacle to stellar birth. It is the prerequisite for it. Stars form because the gas is cold enough to fall inward. As the collapse proceeds, gravitational potential energy converts to heat. The cloud's center grows denser and hotter. A protostar forms, an opaque hot core still accreting material from the surrounding cloud, not yet hot enough for nuclear fusion, but already radiating in the infrared. Over tens of millions of years for a sun-like star, the protostar's core temperature climbs. At approximately 10 million degrees Kelvin, the proton-proton chain ignites. Fusion begins. A star is born from cold. The temperature at the core of our own sun at ignition, that 10 million degree threshold, is almost exactly the lower bound of the corona's present temperature. The corona sits at 1 million to 3 million degrees. The core where fusion occurs sits at 15 million degrees. The surface between them, the photosphere, sits at 5,500 degrees. The sun is a layered thermal structure of extraordinary complexity, in which the coldest layer is not the outermost but the visible surface itself, sandwiched between the cooler photosphere below and the million-degree corona above, surrounded at all distances by the near absolute zero of the vacuum it cannot warm. The aurora australis photographed from the International Space Station above Antarctica, those curtains of green and red light shimmering at altitudes of 100 to 300 kilometers, are the direct visual consequence of the sun's corona being too hot to contain itself. Coronal plasma escaping as solar wind, directed by Earth's magnetic field into the polar regions, colliding with atmospheric oxygen and nitrogen at high altitudes, exciting their electrons to higher energy states, releasing photons as those electrons fall back to ground state. The green emission at 557.7 nanometers is oxygen. The red above 200 kilometers is also oxygen, at a lower density where collisions are rare enough for a slower emission to occur. The blue and purple tones at lower altitudes are nitrogen. The aurora are not decorative. They are a thermometer. Their intensity, their latitude, their color distribution all encode information about the energy delivered by the solar wind, which encodes information about the state of the corona, which encodes information about the magnetic activity of the sun's interior. Every solar storm that produces a major auroral display is a direct message from the thermonuclear engine 93 million miles away, transmitted through the vacuum that cannot itself be warmed, arriving at Earth's magnetic doorstep as a billion-ton cloud of magnetized plasma traveling at hundreds of kilometers per second. The cold of space is not passive. It is the medium through which the sun speaks. And in that medium, in that near-perfect vacuum at near absolute zero, the fate of every photon, every proton, every coronal mass ejection eventually converges on the same destination. Energy disperses, temperature gradients flatten, the universe expands, and as it expands, it cools. The cosmic microwave background cools further with each passing billion years. It's 2.7 Kelvin dropping toward the asymptotic near zero of a universe in which the last stars have exhausted their fuel. The last black holes have evaporated through Hawking radiation, and the thermal energy that once powered 15 million degree stellar cores has spread so thinly across so vast a volume that no gradient remains, no direction for heat to flow, no engine left to run. That state is called heat death. It is the universe's thermal destination, written into the second law of thermodynamics, inevitable on timescales so vast they defeat all analogy. The sun's fire and the cold of space are not opposites in opposition. They are two phases of the same process, the slow, irreversible flow of energy from concentration to diffusion, from hot to cold, from structure to equilibrium. The sun burns. The void is cold. The distance between them is the story of everything. There is a number that appears in the equations of thermodynamics with the quiet authority of something that has always been true, waiting only to be discovered. It is not a large number. It is not dramatic in the way that 15 million degrees or 380 septillion watts is dramatic. It is expressed simply as the letter K, and it bears the name of the Austrian physicist Ludwig Boltzmann, who spent much of his life trying to convince a skeptical scientific community that it was real. Boltzmann's constant, approximately 1.38 times 10 to the minus 23rd joules per Kelvin, is the bridge between the microscopic and the macroscopic. It connects the temperature of a gas, which is a bulk property measurable with an ordinary thermometer, to the average kinetic energy of the individual atoms and molecules that constitute it. Temperature, in Boltzmann's framework, is not a fundamental property of matter. It is a statistical description, an average over an enormous number of individual particle energies, each distributed according to a probability function that depends on the temperature itself. What we call heat is the aggregate behavior of particles in motion. What we call cold is the aggregate behavior of particles nearly still. Boltzmann understood, earlier and more clearly than almost anyone of his era, where the second law of thermodynamics pointed. Entropy, the measure of disorder, or more precisely the measure of the number of microscopic configurations available to a system, always increases in an isolated system. Heat flows from hot to cold because the configurations available to a system with two regions at equal temperature vastly outnumber the configurations available when energy is concentrated in one region. Equilibrium is not a special state. It is simply the most probable state, overwhelmingly so. The universe tends toward equilibrium for the same reason that a dropped glass tends to shatter rather than assemble. There are vastly more ways to be disordered than ordered, and time explores all the available configurations with perfect impartiality. The sun is a temporary interruption of that tendency. It is a region of the universe where, by the accident of gravitational collapse 4.6 billion years ago, an enormous quantity of hydrogen was compressed tightly enough and heated intensely enough that nuclear fusion ignited, creating a sustained, self-regulating energy source that has been delaying the local march toward equilibrium ever since. The energy produced in the core travels outward, warms the photosphere, radiates into space, and disperses. Every photon that leaves the sun carries a fragment of the nuclear binding energy released when 4 hydrogen nuclei fused into 1 helium nucleus. That fragment travels through the cold vacuum, strikes a surface somewhere, a planet, a dust grain, the retina of a living organism, and its energy is absorbed, degraded, redistributed. Entropy increases. The system moves one infinitesimal step closer to equilibrium. Earth intercepts approximately 1 part in 2 billion of the sun's total energy output. That fraction, arriving at the top of the atmosphere at approximately 1,361 watts per square meter, a value known as the solar constant, drives every weather system, every ocean current, every photosynthetic reaction, every wind that has ever blown across the planet's surface. The entire biosphere, from the first photosynthetic bacteria in the Archean Ocean to the forests currently covering 30% of Earth's land surface, is powered by that 1 part in 2 billion. Life on Earth is a thermodynamic consequence of the temperature difference between the sun's photosphere and the cold of space. Organisms are engines that run on that gradient, converting low-entropy solar photons into biological structure, releasing high-entropy heat and long-wavelength infrared radiation back to space. The physicist Erwin Schrödinger, writing in his 1944 book What is Life, described living organisms as systems that feed on negative entropy, that actively maintain their internal order against the thermodynamic tendency toward disorder by consuming free energy from their environment and exporting entropy outward. The sun provides that free energy to Earth. The cold of space provides the sink into which Earth's entropy is ultimately discharged. Without the temperature differential between the sun's surface and the cosmic background, without the 5,500 degrees on one side and the 2.7 Kelvin on the other, the thermodynamic gradient that powers life would not exist. This is not a philosophical statement. It is a direct consequence of the second law. A planet in thermal equilibrium with its surroundings, receiving as much energy as it radiates, at the same temperature throughout, has no free energy available to drive chemistry, geology, or biology. Earth is not in equilibrium with space. It is perpetually out of equilibrium, maintained in that condition by the continuous input of solar radiation. The moment the sun extinguishes, that input stops. Earth's surface begins to cool. Within weeks, the oceans begin to freeze from the surface downward. Within a year, the atmospheric temperature at the surface drops below the freezing point of carbon dioxide. Within tens of thousands of years, Earth reaches a new equilibrium temperature, approximately minus 270 degrees Celsius, warmed only by the faint glow of distant starlight and the residual heat flowing from its own radioactive interior. Cold, still, dark. The sun will not extinguish suddenly. It will follow a trajectory already written in the physics of stellar evolution, a trajectory that has been read from the properties of thousands of other stars at various stages of their lives, so that the sun's future is not a guess, but an inference of high confidence. In approximately 5 billion years, the hydrogen in the sun's core will be sufficiently depleted that the proton-proton chain can no longer sustain the core's pressure against gravitational collapse. The core will contract and heat further. The outer layers will expand as the increased core energy output pushes them outward. The sun will become a red giant, its radius expanding to perhaps 150 to 200 times its current size, its surface temperature cooling to approximately 3,000 to 4,000 Kelvin, as the same luminosity is spread across a vastly larger surface area. At maximum red giant expansion, the sun's surface will extend to approximately the current orbit of Earth, perhaps beyond it, depending on how mass loss during the giant phase affects the orbital dynamics. Earth, if it survives without being engulfed, will be subjected to a solar flux roughly 5,000 times its current value. The oceans will long since have evaporated. The atmosphere will have been stripped away. The surface will be a molten, irradiated rock. After the red giant phase, the sun will shed its outer layers as a planetary nebula, an expanding shell of gas and dust illuminated by the hot stellar remnant at the center. That remnant is a white dwarf, a sphere of electron-degenerate carbon and oxygen approximately the size of Earth, containing roughly half the Sun's current mass, with no ongoing nuclear reactions. It radiates stored thermal energy into space, cooling over billions of years. A white dwarf, then a yellow dwarf, then a brown dwarf, then eventually a black dwarf, a cold, dark, inert mass indistinguishable from the space around it. No black dwarf is believed to exist yet in the observable universe. The universe is approximately 13.8 billion years old. The cooling time for a white dwarf to reach black dwarf status, at the luminosities they radiate, is estimated to exceed the current age of the universe by many orders of magnitude. The first black dwarfs will not form for trillions of years. The sun's fire, in that sense, will outlast comprehension. Boltzmann did not live to see his ideas vindicated in the detail they deserved. He died by suicide in 1906, despondent over years of hostility from physicists who rejected the atomic theory of matter and the statistical interpretation of thermodynamics he had spent his career developing. Within a few years of his death, Einstein's analysis of Brownian motion in 1905 and Jean Perrin's experimental confirmation shortly after established beyond any serious doubt that atoms were real, that statistical mechanics was correct, and that Boltzmann's framework was the foundation of a thermodynamics that described the universe from the quantum scale to the cosmological. His tombstone in Vienna carries his entropy formula, S equals K log W, the most consequential equation in the science of heat, carved in stone above the man who derived it and could not be persuaded to wait for the world to understand. The cosmic microwave background, that 2.7 Kelvin glow permeating all of space, the universe's oldest light, was released approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time, allowing photons to travel freely rather than scattering continuously off the dense charged plasma. Those photons have been traveling ever since, stretched by the expansion of space from visible light to microwave radiation, cooling as the universe expanded. They arrive today from every direction simultaneously, a perfect thermal record of the universe's early state imprinted on the sky. The fact that the background is almost perfectly uniform, with temperature variations of only 1 part in 100,000, reflects the extraordinary uniformity of the early universe. Those tiny variations are the seeds of everything that followed. The slight over-densities that gravity amplified over hundreds of millions of years into the first stars, the first galaxies, the filamentary large-scale structure of the universe visible today, the spiral arms where molecular clouds collapse into stellar nurseries, the stellar nurseries where cold gas contracts into protostars, the protostars where cores heat to 10 million degrees and fusion ignites. The cold of space made the hot stars possible. Structure emerged from near-perfect uniformity through the action of gravity on a gas just slightly uneven, in a universe just cold enough for the unevenness to matter. The Sun is 4.6 billion years old and halfway through its main sequence lifetime. It has fused approximately 100 Earth masses of hydrogen into helium since it ignited, and it carries enough hydrogen in its core to continue fusing for approximately another 5 billion years. In cosmic terms, it is middle-aged, unremarkable, a G-type main sequence star of average mass and luminosity, among the estimated 2 trillion galaxies each, containing hundreds of billions of stars, visible in the observable universe. There is nothing singular about it except one thing. From the third planet in its system, at a distance of 150 million kilometers, across a vacuum maintained at 2.7 Kelvin by the expansion of the universe itself, a species evolved from the chemistry of solar-powered photosynthesis has looked outward and asked why the sun is hot and space is cold. The answer required the second law of thermodynamics, nuclear physics, quantum mechanics, helioseismology, neutrino physics, magnetohydrodynamics, spacecraft instrumentation, and nearly 2 centuries of accumulated scientific inquiry across dozens of disciplines in dozens of countries by thousands of researchers. The answer is still not entirely complete. The corona remains incompletely explained. The nanoflare budget has not been directly confirmed. The switchbacks measured by the Parker Solar Probe await a full theoretical account. What is known is this: the universe began hot and has been cooling ever since. Gravity, working against that cooling, periodically concentrates matter and rekindles fire in the dark. Those fires, Stars pour energy into the void, warming every surface they reach and leaving the vacuum between them exactly as cold as it was before. The heat does not accumulate in space. It disperses. It spreads. It fades toward the 2.7 Kelvin floor, and below it toward the asymptotic cold of a universe approaching, but never quite reaching, for spans of time that dwarf all human reckoning, its final stillness. The sun rises because the universe has not yet finished cooling. That is all. That is everything.